Tonight, we're going to go somewhere almost no one has ever been. Not into space, not to another galaxy. We're going inward, deep inside the fabric of matter itself, because right now, buried beneath everything you see, everything you touch, everything you are, there appears to be a hidden layer. A structure beneath a structure, and the experiments happening at CERN, where particles are smashed together at nearly the speed of light, are beginning to pull back the curtain on something that could reshape our entire understanding of reality. The measurements are coming in. Some of them match what physicists predicted, and some of them do not. And those mismatches, those tiny cracks in our most successful theory, may be the first glimpse of something we have never seen before. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It is a small thing for you, but it makes a huge difference for me. Now, let's begin. Let us start with something you already know. Matter. The stuff of the world. The chair you're sitting on. The phone in your hand. The air filling your lungs right now. Your body itself. All of it is matter. And for most of human history, we had absolutely no idea what matter actually was. We could describe it. We could shape it and melt it and burn it and build things out of it. But the question of what it is made of, what it truly is at the deepest level, remained a mystery for thousands of years. And that mystery turned out to be far deeper and far stranger than anyone imagined. The first person we know of who seriously proposed an answer was a Greek philosopher named Democritus, who lived around 460 years before the Common Era. Democritus suggested that if you kept cutting matter into smaller and smaller pieces, eventually you would reach something that could not be cut any further. He called these pieces atomos, which in Greek means uncuttable. It was a brilliant idea. Simple, elegant, and logical. If you break a rock in half, you get 2 smaller rocks. Break those in half, you get 4 even smaller pieces. Keep going. At some point, Democritus reasoned, you must reach a piece so small that it cannot be divided any further. That would be the fundamental building block of everything. It was also completely untestable at the time. Democritus had no microscope, no laboratory, no way to verify his hypothesis. It was pure philosophical reasoning. And because of that, it was largely set aside for over 2,000 years. Aristotle, whose ideas dominated Western thought for centuries, rejected atomism in favor of a theory that all matter was made of 4 elements: earth, water, air, and fire. These elements could transform into one another, mix in different proportions, and combine to create the variety of substances we observe in the world around us. It was wrong, but it was the dominant view for an extraordinarily long time. Entire civilizations rose and fell while people still believed that everything was made of 4 basic elements. Alchemists spent centuries trying to transform lead into gold based on this mistaken framework. It was not until the scientific revolution that humanity began to seriously question these ancient assumptions and develop the tools to test them. The idea of atoms did not become a serious scientific proposal until the early 1800s, when an English chemist named John Dalton revived it. Dalton noticed something remarkable about chemical reactions. Elements always combined in fixed, predictable ratios. Hydrogen and oxygen always combined in a specific proportion to make water. Carbon and oxygen always combined in a specific proportion to make carbon dioxide. No matter how many times you ran the experiment, the ratios were always the same. This made perfect sense if elements were composed of tiny indivisible particles, each with a specific mass, Different elements had particles of different masses, and chemical reactions were simply rearrangements of these particles into new configurations. Dalton's atomic theory was one of the great leaps in scientific understanding. It took Democritus's ancient philosophical speculation and turned it into a testable, predictive framework that could explain the patterns chemists were observing in their laboratories every day. But here is where the story starts to get truly interesting, because atoms turned out not to be uncuttable after all. In 1897, a British physicist named Joseph John Thomson discovered the electron. He was experimenting with cathode rays, streams of particles produced inside vacuum tubes when an electric current was passed through them. Thomson found that these rays were made of incredibly tiny particles carrying a negative electric charge. These particles were much, much smaller than any atom. They came from inside atoms. This was a shock to the scientific community. If atoms contained smaller particles within them, then atoms were not fundamental. They had internal structure. They could be taken apart. The thing that was supposed to be uncuttable could, in fact, be cut. Thomson proposed a model of the atom that became known as the plum pudding model. He imagined the atom as a uniform sphere of positive charge with negatively charged electrons embedded throughout it, like plums scattered through a pudding. It was a reasonable guess given what he knew at the time. The atom had to be electrically neutral overall, since matter is normally uncharged. So the negative electrons had to be balanced by something positive. Thomson imagined that positive charge spread smoothly throughout the atom. But he was wrong. In 1911, a New Zealand-born physicist named Ernest Rutherford performed one of the most famous experiments in the history of science. Working at the University of Manchester with his assistants Hans Geiger and Ernest Marsden, he directed a beam of alpha particles, which are essentially helium nuclei carrying a positive charge, at a thin sheet of gold foil only a few hundred atoms thick. If Thomson's plum pudding model was correct, the alpha particles should have passed through the foil with only slight deflections. The positive charge in the atom was supposed to be spread out, so there would be nothing dense enough to deflect the alpha particles significantly. Most of the alpha particles did pass straight through the foil as if it were not even there. But a tiny fraction of them, roughly 1 in 8,000, bounced back at large angles, and a few even bounced almost straight back toward the source. Rutherford was stunned. He later said it was as remarkable as if you had fired a 15-inch artillery shell at a piece of tissue paper and it came back and hit you. The only way to explain this result was if the positive charge and nearly all the mass of the atom were concentrated in an incredibly tiny, dense core at the CERN center. Rutherford had discovered the atomic nucleus. The nucleus is extraordinarily small compared to the atom it sits inside. If you scaled an atom up to the size of a football stadium, the nucleus would be about the size of a marble sitting at the center of the field. Everything else, all the vast space between the nucleus and the orbiting electrons, is empty. This means that atoms, and by extension all matter, are almost entirely empty space. The solid feel of the table beneath your hands, the hardness of a rock, the firmness of the ground beneath your feet, none of it comes from actual solid material packed tightly together. It comes from electromagnetic forces between atoms, forces that resist compression and give the illusion of solidity. But at the atomic level, what you think of as solid matter is overwhelmingly nothing at all. The nucleus itself turned out to contain two types of particles: protons, which carry a positive electric charge, and neutrons, which carry no electric charge. Protons were identified by Rutherford in 1919 when he demonstrated that hydrogen nuclei could be knocked out of nitrogen atoms by bombarding them with alpha particles. He had achieved the first artificial transmutation of one element into another, something alchemists had dreamed of for centuries. Neutrons were discovered by James Chadwick in 1932, when he identified an electrically neutral particle with nearly the same mass as the proton being emitted from beryllium targets struck by alpha particles. Chadwick won the Nobel Prize for this discovery just 3 years later. For a while, this seemed like it might be the bottom of the rabbit hole. Atoms are made of electrons, protons, and neutrons. Protons and neutrons are packed into the nucleus. Electrons orbit the nucleus at relatively enormous distances compared to the size of the nucleus itself. 3 particles, clean and simple. Maybe this was it. Maybe these 3 particles were truly fundamental. The real uncuttable building blocks that Democritus had imagined over 2,000 years earlier. But it was not the end. Not even close. Starting in the late 1940s and accelerating through the 50s and 60s, physicists began smashing protons and neutrons together at higher and higher energies in machines called particle accelerators. These machines used powerful electric and magnetic fields to push particles to enormous speeds before slamming them into targets or into each other. And what physicists found in these collisions was bewildering. Every time they pushed to higher collision energies, new particles came flying out of the wreckage. Not just fragments of the original particles, but entirely new types of particles that had never been seen before. Pions, kaons, lambda particles, sigma particles, Xi particles, delta particles, eta particles, omega particles. The list kept growing and growing. By the early 1960s, there were hundreds of supposedly fundamental particles. Physicists jokingly called it the particle zoo, and it was as confusing as it sounds. Enrico Fermi reportedly quipped that if he had wanted to memorize the names of particles, he would have become a botanist. This chaotic zoo of particles was confusing, but it also hinted at something important. If there were so many different types of particles, maybe they were not all truly fundamental. Maybe they, like atoms before them, had internal structure. Maybe they were made of something even smaller. History was repeating itself. Every time physicists thought they had found the fundamental building block, it turned out to have parts. In 1964, 2 physicists working independently proposed a solution that would bring order to the chaos. Murray Gell-Mann at the California Institute of Technology and George Zweig at CERN both suggested that protons, neutrons, and all those hundreds of other particles were not fundamental at all. They were made of smaller constituents. Gell-Mann called them quarks, a whimsical name he borrowed from a passage in James Joyce's experimental novel Finnegan's Wake. Zweig called them aces. The physics community went with quarks. The quark model was elegant and powerful. It proposed that protons are made of 3 quarks, specifically 2 up quarks and 1 down quark. Neutrons are also made of 3 quarks, 2 down quarks, and 1 up quark. And all those hundreds of strange particles in the particle zoo were just different combinations of a small number of quark types. Different arrangements of the same building blocks, much like different words are different arrangements of the same 26 letters in the alphabet. The model explained the patterns beautifully. hundreds of seemingly unrelated particles suddenly made sense as combinations of a handful of fundamental constituents. Particles that appeared to have nothing in common turned out to be cousins, different arrangements of the same underlying quarks. But there was a problem, a serious one. Nobody had ever seen an individual quark, and as it turned out, nobody ever would. Quarks have a peculiar property that sets them apart from anything else in physics. They cannot exist alone. They are permanently confined inside larger composite particles by one of the fundamental forces of nature called the strong nuclear force. The strong force is carried by particles called gluons, and it has a deeply counterintuitive characteristic that makes it unique among all the forces we know of. Unlike gravity or electromagnetism, which get weaker as you move farther from the source, the strong force actually gets stronger as quarks are pulled apart. Imagine stretching a rubber band. The farther you pull, the harder it pulls back. The strong force is like that, except the rubber band never breaks. Try to separate two quarks and the force between them increases. Pull harder and it increases more. Eventually the energy you are putting into trying to separate them becomes so enormous that it is converted into mass, creating brand new quarks from the vacuum of space itself, in accordance with Einstein's relationship between energy and mass. These newly created quarks immediately pair up with the ones you were trying to isolate, forming new composite particles. You end up with more particles, but never with a lone quark sitting by itself. This phenomenon is called color confinement, and it is one of the most remarkable and unusual features of any fundamental force in nature. Despite the fact that individual quarks have never been directly isolated, the evidence for their existence is overwhelming and comes from multiple independent lines of investigation. The most dramatic confirmation came from experiments at the Stanford Linear Accelerator Center, known as SLAC, in the late 1960s and early 1970s. Physicists there fired high-energy electrons at protons and carefully measured how the electrons scattered. If the proton were a smooth, uniform blob of matter, the electrons would scatter in a gentle, predictable pattern. Instead, the electrons bounced off hard, point-like internal structures within the proton, scattering at large angles in a way that could only be explained if the proton contained small, dense objects inside it. These experiments, called deep inelastic scattering experiments, were essentially a replay of Rutherford's gold foil experiment at a far deeper level of reality. Rutherford found a nucleus hidden inside the atom. The SLAC experiments found quarks hidden inside the proton. The three experimenters who led this work, Jerome Friedman, Henry Kendall, and Richard Taylor, won the Nobel Prize in Physics in 1990 for their discovery. Their results, combined with an enormous body of supporting evidence from particle physics experiments conducted around the world over the following decades, confirmed beyond any reasonable doubt that quarks are real, physical objects. They exist inside protons and neutrons, permanently bound together by the exchange of gluons through the strong force. So here is where our understanding of matter stood by the late 20th century. Everything around you is made of atoms. Atoms are made of electrons orbiting a nucleus. The nucleus is made of protons and neutrons. Protons and neutrons are made of quarks held together by gluons. And as far as any experiment has ever been able to determine, quarks and electrons appear to be truly fundamental. They show no signs of internal structure whatsoever. No experiment has ever detected anything smaller inside them, down to the smallest scales we can currently probe. This comprehensive understanding, this detailed description of what matter is made of and exactly how it behaves, is captured in what physicists call the standard model of particle physics. And the standard model is not just another scientific model among many. It is the single most precise and extensively tested scientific theory ever constructed by human beings in the entire history of our species. Its predictions have been confirmed to accuracies of better than 1 part in 10 billion in certain measurements. No other theory in any field of science has ever achieved that level of agreement between prediction and observation. Not Newtonian mechanics, not general relativity, not any theory in biology, chemistry, geology, or any other discipline. The standard model stands alone in its precision. The standard model contains 17 fundamental particles. There are 6 quarks, arranged in 3 pairs called generations. The first generation contains the up quark and the down quark, which are the building blocks of protons and neutrons, and therefore of all ordinary atomic matter. The second generation contains the charm quark and the strange quark. The third generation contains the top quark and the bottom quark. These heavier quarks are unstable and quickly decay into lighter quarks, which is why they are not found in ordinary matter. They only appear briefly in high-energy collisions or certain radioactive decays. There are also 6 leptons, similarly arranged in 3 generations. The first generation contains the electron, which orbits the nucleus in atoms, and the electron neutrino, a ghostly particle with almost no mass that barely interacts with anything. The second generation contains the muon, which is essentially a heavier version of the electron, about 207 times more massive, and the muon neutrino. The third generation contains the tau, heavier still at about 3,490 times the electron's mass, and the tau neutrino. Then there are 4 force-carrying particles called gauge bosons. The photon carries the electromagnetic force and is the particle of light. The W boson and the Z boson carry the weak nuclear force, which is responsible for certain types of radioactive decay. And 8 types of gluons carry the strong nuclear force that binds quarks together inside protons and neutrons. Finally, there is the Higgs boson, which plays a unique and crucial role that we will explore shortly. These 17 particles and the mathematical rules governing their interactions account for virtually everything we observe in the physical world. Every chemical reaction that has ever occurred, every nuclear process that powers the stars, every beam of light that has ever illuminated anything, the firing of neurons in your brain as you process these words right now. All of it traces back to the interactions of these 17 particles through 3 fundamental forces. The standard model describes 3 of the 4 known forces of nature. Electromagnetism governs the behavior of electrically charged particles and is responsible for light, chemistry, the structure of atoms, and essentially all of the technology that modern civilization depends on. The strong nuclear force binds quarks together inside protons and neutrons and holds atomic nuclei together against the electromagnetic repulsion between their positively charged protons. The weak nuclear force is responsible for certain types of radioactive decay and plays a critical role in the nuclear fusion reactions that power the sun and every other star in the universe. The fourth force, gravity, is conspicuously absent from the standard model. Einstein's general theory of relativity describes gravity beautifully at large scales, but it is fundamentally incompatible with the quantum framework that describes the other three forces. We will return to this mystery later. Even without gravity, the Standard Model has a track record of prediction that is nothing short of extraordinary. The W and Z bosons were predicted in the 1960s by theorists Sheldon Glashow, Abdus Salam, and Steven Weinberg, who showed that electromagnetism and the weak nuclear force could be unified into a single electroweak force at high energies. The W and Z bosons were then discovered experimentally at CERN in 1983. The top quark was predicted by the pattern of the quark generations and discovered at Fermilab in 1995. And the Higgs boson, the final missing piece of the Standard Model, was predicted in 1964 and discovered at CERN in 2012 after a search that lasted nearly half a century. Every time the Standard Model has stuck its neck out with a prediction, experiment has confirmed it. Now, to test these predictions with the extraordinary precision required, and to search for whatever physics might exist beyond the Standard Model, humanity needed to build something unprecedented. A machine capable of accelerating particles to within a whisper of the speed of light and smashing them together with enough concentrated energy to recreate conditions that have not existed naturally in the universe for over 13 billion years. That machine is the Large Hadron Collider. The LHC is housed at CERN, the European Organization for Nuclear Research, straddling the border between Switzerland and France near Geneva. Inside a circular tunnel roughly 27 kilometers in circumference, buried about 100 meters underground, two beams of protons travel in opposite directions at 99.9999991% of the speed of light. They are guided around this enormous ring by more than 1,700 superconducting magnets cooled to 1.9 kelvins, colder than the vacuum of outer space. At 4 points around the ring, the beams cross and protons collide head-on. The energy concentrated in each collision recreates for an instant the conditions that existed about 1 trillionth of a second after the Big Bang. When two protons collide at these energies, they do not simply bounce off each other, they effectively disintegrate. The quarks and gluons inside them interact directly, and the colossal energy of the collision is converted into matter. New particles, some of which have not existed naturally since the first moments of the universe, are briefly conjured from pure energy. They live for unimaginably short durations, sometimes a trillionth of a second, before decaying into cascades of lighter particles. The detectors surrounding the collision points, enormous instruments weighing thousands of tons and containing millions of individual sensors, capture these cascades and allow physicists to reconstruct what happened in the collision. The LHC generates roughly 600 million collisions every second. The vast majority produce familiar, well-understood results. But occasionally, buried in that torrent of data, something unexpected appears. A measurement that deviates from the Standard Model's prediction. A pattern that hints at new physics. Finding these rare signals requires processing about 1 petabyte of data per day, distributed across 170 computing centers in over 40 countries. The journey from Democritus to the Large Hadron Collider spans nearly 2,500 years of human curiosity. At every stage, we peeled back another layer of reality and found something stranger and more beautiful beneath. Atoms were not uncuttable. The nucleus was hiding inside. Quarks were hiding inside the nucleus. And now we are asking the next question. The question that has driven physics forward at every turn. Is this truly the bottom? Or is there something else hiding beneath what we have found? Something we have not yet seen? Something that the Standard Model, for all its extraordinary success, does not describe? Something that would represent the next hidden layer in the structure of matter itself. And for the first time, the data are beginning to whisper an answer. Here is something that will fundamentally change how you think about the physical world. The particles we just discussed, the quarks, the electrons, the gluons, the photons, all of them are not the most fundamental things in nature. They are not the bedrock of reality. They are consequences of something deeper, something invisible, something that fills every cubic centimeter of space in the entire universe, including the space inside your body, inside your brain, inside every atom of every object you have ever touched, or seen, or imagined. That something is called a quantum field. This idea is so central to modern physics, and so different from how most people think about the world, that it is worth taking the time to understand it properly. Because once you grasp what quantum fields are, you will never look at matter the same way again. You will realize that the solid, tangible world you experience every day is built on something that is neither solid nor tangible. It is built on invisible fields that stretch across the entirety of space and time. And understanding these fields is the key to understanding why physicists believe there may be a hidden layer beneath everything the Standard Model describes. To understand what a quantum field is, let us start with something familiar. Think about an ocean. A vast, calm ocean stretching out in every direction as far as you can see, perfectly still. Now imagine dropping a stone into that ocean. A ripple spreads outward from the point of impact. A wave. That wave is not a separate thing from the ocean. It is a disturbance in the ocean, a temporary configuration of the water. The wave moves across the surface and it has properties you can measure. It has a height. It has a wavelength. It has a speed. You can point to it and say there is a wave right there. But the wave is not made of something different from the ocean. It is the ocean, momentarily arranged in a particular pattern. Now here is the insight that transformed 20th century physics and reshaped our understanding of what matter actually is. Particles are like waves on an ocean. And the ocean is the quantum field. An electron is not a tiny ball of matter floating through empty space, like a miniature planet orbiting an atomic sun. An electron is a localized excitation, a specific kind of vibration, in something called the electron field, which extends through all of space. A photon is not a tiny packet of light traveling through a void. A photon is a localized excitation in the electromagnetic field. A quark is a ripple in the quark field. A gluon is a ripple in the gluon field. Every type of particle in the Standard Model corresponds to its own quantum field. And what we call a particle is simply what happens when one of these fields gets disturbed in a particular way at a particular location. The particle is not the fundamental thing. The field is... This framework is called quantum field theory, and it is not a speculation or a philosophical interpretation or a metaphor. Every prediction the Standard Model makes, every calculation that agrees with the experiment to 10 decimal places, is a calculation performed using quantum field theory. When physicists say the Standard Model is the most successful theory in the history of science, what they really mean is that quantum field theory applied to a specific set of fields and interactions is the most successful theory in the history of science. What does it actually mean to say that space is filled with quantum fields? It means that even apparently empty space, what you might think of as a perfect vacuum with absolutely nothing in it, is not really empty. It is permeated by these fields. Every single point in the universe has a value for the electron field, for each of the quark fields, for the electromagnetic field, for the Higgs field, and for every other field in the Standard Model. In a vacuum, these fields are at their lowest energy state. They are quiet, undisturbed, but they are there. They are always there. You cannot remove them. You cannot turn them off. They are not things that exist in space. They are part of the structure of space itself. And even in their quieter state, these fields are not perfectly still. This is where quantum mechanics enters the picture and makes everything stranger. The Heisenberg uncertainty principle, one of the foundational results of quantum mechanics, states that certain pairs of physical properties cannot both be precisely zero at the same time. Applied to quantum fields, this means that even in a vacuum, even when no particles are present, the fields fluctuate. They jitter. They vibrate slightly around their lowest energy state. These fluctuations are called vacuum fluctuations, and they are not theoretical abstractions. They are real. They have been measured. They produce physical effects that you can detect in a laboratory. One of the most striking demonstrations of vacuum fluctuations is the Casimir effect. In 1948, the Dutch physicist Hendrik Casimir predicted that if you place two uncharged, perfectly conducting metal plates very close together in a vacuum, the vacuum fluctuations of the electromagnetic field between the plates would differ from those outside the plates. The restricted space between the plates cannot support all the same fluctuation modes that the unrestricted space outside can. This imbalance creates a net force that pushes the plates together. It is a tiny force, incredibly tiny, but it is real. In 1997, Steve Lamoureux at the University of Washington in Seattle measured this force directly, confirming Casimir's prediction to within about 5% accuracy. Empty space, through its quantum fields, exerts a measurable physical force on objects. Another measurable consequence of vacuum fluctuations is the Lamb shift. In 1947, Willis Lamb and Robert Rutherford at Columbia University measured a tiny difference in the energy levels of the hydrogen atom that could not be explained by the existing quantum mechanical theory of the time. The two energy levels that should have been identical according to the Dirac equation turned out to differ by a small but measurable amount. The explanation, worked out by theorists including Hans Bethe, Julian Schwinger, Richard Feynman, and Shinichiro Tomonaga, was that the electron in the hydrogen atom is constantly interacting with the vacuum fluctuations of the electromagnetic field surrounding it. The electron does not simply orbit the proton in a clean, undisturbed path. It is buffeted by the invisible jittering of the quantum field, and those interactions shift its energy by a tiny but real amount. This calculation and its agreement with Lamb's measurement was one of the great triumphs of quantum electrodynamics and helped establish quantum field theory as the correct framework for describing nature at the subatomic level. Schwinger, Feynman, and Tomonaga shared the Nobel Prize in Physics in 1965 for this work. These effects are not exotic phenomena confined to specialized laboratories. Vacuum fluctuations are happening everywhere, all the time, right now, inside every atom of your body, in the air around you, in the space between galaxies. The quantum fields are always present, always fluctuating, always subtly influencing the behavior of every particle in the universe. The world you experience, the seemingly solid, stable world of tables and chairs and rocks and trees, is built on top of an invisible, constantly vibrating fabric of quantum fields. Now, among all the quantum fields in the Standard Model, there is one that stands apart from all the others. One that plays a role unlike any other field in physics. One that was predicted to exist in 1964, but was not directly confirmed until 2012, nearly half a century later. That field is the Higgs field, and understanding it is essential to understanding why physicists believe there is a hidden layer beneath matter. The Higgs field is different from every other quantum field because it does something no other field does. It gives mass to other particles. This might not sound dramatic at first, but think about what it implies. Without the Higgs field, electrons would have no mass. Quarks would have no mass. The W and Z bosons that carry the weak nuclear force would have no mass. And if these particles had no mass, the universe as we know it could not exist. Massless electrons could not be captured into orbits around nuclei. Atoms could not form. Without atoms, there would be no chemistry. Without chemistry, there would be no molecules, no proteins, no DNA, no cells, no life. Stars would burn differently. The forces of nature would behave differently. The entire structure of the physical world depends on particles having the specific masses they have. And those masses come from the Higgs field. Here is how it works, simplified but faithful to the actual physics. Different particles interact with the Higgs field with different strengths as they move through space. Particles that interact strongly with the Higgs field acquire a large mass. The top quark, for instance, interacts very strongly with the Higgs field and has a mass roughly 184 times that of a proton, making it the heaviest known fundamental particle. Particles that interact weakly with the Higgs field acquire a small mass. The electron interacts relatively weakly, giving it a mass only about 1/1800th that of a proton. And some particles do not interact with the Higgs field at all. Photons, for instance, pass through the Higgs field without any interaction whatsoever. They remain massless and consequently travel at the speed of light. This is not a coincidence. It is a direct consequence of their relationship with the Higgs field. A photon has no mass because it does not couple to the Higgs field. An electron has mass because it does. You will sometimes hear an analogy comparing the Higgs field to a room full of people at a party. If a celebrity walks in, everyone clusters around them, slowing their movement. That resistance to motion is like mass. If an unknown person walks in, nobody pays attention, and they move through easily. That is like having a small mass. And if someone invisible walks in, they pass through the crowd at full speed without anyone noticing. That is like a photon, massless and traveling at the speed of light. The Higgs field is that crowd, filling all of space, and the degree to which each particle interacts with it determines how much mass that particle carries. The analogy is helpful for building intuition, but it leaves out something crucial about the Higgs field. Something that makes it truly unique among all known fields. In its lowest energy state, the state it naturally settles into, the Higgs field has a non-zero value everywhere in the universe. This is profoundly different from every other quantum field. The electromagnetic field, when there are no photons around, has a value of 0. The electron field, when there are no electrons around, has a value of 0. Every other field in the Standard Model sits at 0 in its ground state, but the Higgs field does not. Even in a perfect vacuum, with no particles of any kind present, the Higgs field has a constant, non-zero value permeating all of space. It is always on, always present, always providing mass to every particle that interacts with it. This non-zero vacuum value is connected to one of the deepest and most beautiful ideas in modern physics: spontaneous symmetry breaking. The equations that describe the Standard Model possess a high degree of mathematical symmetry. In their most natural form, all particles are massless. The weak nuclear force and electromagnetism are unified into a single electro-weak force. Everything is symmetric and elegant, but this perfectly symmetric state is unstable. It is like a ball balanced perfectly on the tip of a hill. Mathematically possible, but physically unstable. The slightest disturbance will cause the ball to roll down into the valley. The Higgs field settling into its non-zero value is like the ball rolling into the valley. The field falls into a lower energy state, and in doing so, it breaks the symmetry of the equations. The unified electroweak force splits into the electromagnetic force and the weak nuclear force, which now behave differently from each other, and particles that were massless in the symmetric state acquire different masses depending on how strongly they interact with the now non-zero Higgs field. This mechanism was proposed in 1964 by several groups of physicists working independently. A remarkable example of parallel discovery in science. Peter Higgs at the University of Edinburgh published a paper describing how a field with a non-zero vacuum value could give mass to gauge bosons. Francois Engler and Robert Brute at the Free University of Brussels published a closely related paper describing the same essential mechanism. And Gerald Guralnick, Carl Hagen, and Tom Kibble at Imperial College London published a third paper that also described the mechanism and proved an important mathematical theorem about it. All three papers appeared within a span of just a few months. The mechanism became generally known as the Higgs mechanism, and the particle associated with the Higgs field became known as the Higgs boson. But proposing a mechanism and proving it exists are very different things. For nearly half a century after those papers were published, the Higgs boson remained a theoretical prediction, an essential piece of the Standard Model that had never been directly observed. Physicists were confident the mechanism was correct because the rest of the Standard Model fit together so beautifully with it. The electroweak unification of electromagnetism and the weak force, confirmed experimentally in the 1980s, essentially required something like the Higgs mechanism to work, but confidence is not proof. Without directly producing a Higgs boson and measuring its properties, the mechanism remained unconfirmed. The challenge was enormous. Producing a Higgs boson requires concentrating enough energy in a collision to excite the Higgs field and create a ripple in it, just as dropping a heavy enough stone creates a wave in a pond. The Higgs boson turned out to have a mass of about 125 billion electron volts, roughly 133 times heavier than a proton. Creating it required collision energies far beyond what any accelerator in the 1960s, 70s, 80s, or 90s could achieve. The Higgs boson was out of reach. It existed in theory, it had to exist if the Standard Model was correct, but no machine on Earth could create it. This is why the Large Hadron Collider was built. The LHC was designed, in substantial part, specifically to find the Higgs boson. The machine cost approximately $5 billion for the accelerator alone, with billions more spent on its four main detectors, computing infrastructure, and supporting systems. It took over a decade to design and build. Thousands of scientists and engineers from dozens of countries contributed to its construction. It required advances in superconducting magnet technology, cryogenic engineering, vacuum systems, particle detection, and computing that pushed the boundaries of what was technically possible. The LHC was one of the largest, most complex, and most ambitious scientific instruments ever constructed by human civilization. And on the 4th of July, 2012, it delivered. On that day, in a packed auditorium at CERN, physicists from the ATLAS and CMS experiments independently announced that they had each discovered a new particle. The ATLAS collaboration and the CMS collaboration had been running independently, using different detectors with different designs and different analysis techniques, precisely so that they could cross-check each other's results. Both found a particle with a mass of approximately 125 billion electron volts. Both found it with a statistical significance exceeding 5 standard deviations, the threshold that particle physicists use to claim a discovery. The probability of both experiments independently producing such a result by a random chance was astronomically small. Peter Higgs, then 83 years old, was in the audience. He wept. Nearly half a century after he had proposed the field and the mechanism, the particle that bore his name had been found. François Englert was also present. Robert Brute had died in May of 2011, just over a year before the discovery. The Nobel Prize in Physics was awarded in 2013 to Higgs and Englert for their theoretical prediction. Brute, tragically, could not share it. The Nobel Prize is not awarded posthumously. The discovery of the Higgs boson was one of the crowning achievements of modern science. It confirmed that the Higgs field is real, that it permeates all of space, that it gives mass to fundamental particles through the mechanism of spontaneous symmetry breaking. It completed the Standard Model. Every single particle predicted by the theory had now been observed experimentally. The theoretical framework that had been assembled piece by piece over the course of the 20th century was now fully validated by experiment. But here is where the story takes a crucial turn. Because the discovery of the Higgs boson was both a triumph and a provocation. Many physicists had hoped that the Higgs boson, when found, would behave in ways that deviated from the Standard Model's predictions. They hoped it would be heavier or lighter than expected, that it would decay into particles at rates different from what the Standard Model calculated, that its properties would provide clear, unmistakable evidence for new physics beyond the Standard Model. Supersymmetry, extra dimensions, composite Higgs models, many popular theoretical frameworks predicted that the Higgs boson should show signs of something beyond the Standard Model. Instead, the Higgs boson was almost exactly what the Standard Model predicted. Its mass was in the allowed range. Its decay rates, measured with increasing precision over the years following the discovery, matched Standard Model calculations within experimental uncertainties. Its spin and parity quantum numbers were exactly what the Standard Model said they should be. There was no dramatic smoking gun for new physics in the Higgs boson data. For some physicists, this was deeply frustrating. The Standard Model was now complete, but it was also clearly incomplete. It still could not explain dark matter. It still could not explain why the universe contains more matter than antimatter. It still could not account for neutrino masses in a natural way. It still had no description of gravity at the quantum level. The Standard Model was like a beautiful painting with obvious gaps in the canvas. Holes where something clearly should be but is not. The Higgs boson had been found, but it had not pointed the way to whatever fills those gaps. And yet, there is another way to search for new physics. A method that is less dramatic than discovering a brand new particle, but potentially just as powerful. A method that has a long and distinguished history in physics: precision measurement. The idea behind precision measurement is straightforward in principle, but extraordinarily demanding in practice. The Standard Model makes incredibly detailed, highly specific numerical predictions for how particles should behave. Not rough estimates or approximate guidelines, but exact numbers calculated to many decimal places. The mass of the W boson should be a specific value. The magnetic moment of the muon should be a specific value. The rate at which a B meson decays into particular final states should be a specific value. These predictions are not adjustable. Once the input parameters of the Standard Model are fixed by measurement, every other quantity is determined by the mathematics. Now, if you measure one of these quantities with extraordinary precision, with enough decimal places, and your measurement disagrees with the Standard Model's prediction, even by a small amount, it means something is affecting that particle that the Standard Model does not account for. It means there is a force, a field, or a particle that the Standard Model does not include, and its influence is subtly altering the behavior of known particles. This is how new physics has been found before. The anomalous precession of Mercury's orbit, a tiny discrepancy between the observed orbit and what Newton's gravity predicted, was one of the key pieces of evidence that led Einstein to develop general relativity in 1915. The orbit was almost exactly what Newton predicted. Almost, but not quite. And that tiny not quite turned out to be the fingerprint of a completely new understanding of gravity as the curvature of space-time. Similarly, the Lamb shift, that tiny discrepancy in hydrogen energy levels that I described earlier, was a fingerprint of vacuum fluctuations and the quantum nature of the electromagnetic field. The discrepancy was minuscule. It corresponded to a frequency difference of about 1,000 megahertz, tiny compared to the frequencies involved in the hydrogen atom's overall structure. But Willis Lamb measured it, and that measurement opened the door to quantum electrodynamics. The history of physics is filled with examples of tiny discrepancies leading to revolutionary discoveries. A measurement that is almost right, but not quite. A prediction that agrees with observation to 5 decimal places, but disagrees at the 6th. These small cracks in our understanding have repeatedly turned out to be the first glimpses of deeper layers of reality, and this is precisely what is happening now. The LHC, along with other particle physics experiments around the world, is measuring the properties of known particles with extraordinary and ever-increasing precision. Every time a W boson is produced and its mass is measured, every time a muon spirals in a magnetic field and its magnetic moment is recorded, every time a B meson decays and the products of that decay are catalogued, each of these measurements is a test of the Standard Model. Each one is an opportunity to catch the Standard Model making a wrong prediction. Each one is a chance to detect the subtle fingerprint of something new. And here is why this approach is so powerful. When a particle exists in the quantum world, it does not exist in isolation. It constantly interacts with all the quantum fields around it. An electron, for instance, is surrounded by a cloud of virtual photons that it continually emits and reabsorbs. These virtual photons can briefly create virtual electron-positron pairs that pop into existence and then annihilate. And those virtual pairs can interact with other virtual particles. The result is an incredibly complex web of interactions, all happening within the quantum vacuum, all contributing tiny corrections to the electron's measured properties. The standard model accounts for all the virtual particles it knows about. It calculates the contributions of virtual photons, virtual W and Z bosons, virtual quarks, virtual gluons, virtual Higgs bosons. All of these are included in the prediction, but if there are particles or fields that the standard model does not know about, particles that have not yet been discovered, those unknown particles would also contribute to the virtual cloud surrounding every known particle. Their contributions would be tiny because unknown particles are presumably heavy and their effects would be suppressed by their large masses. But they would not be zero. They would shift the measured properties of known particles by small but potentially measurable amounts. This is the power of precision measurement. You do not need to produce the unknown particle directly. You do not need to have enough collision energy to create it. You just need to measure known particles precisely enough to detect the unknown particle's subtle gravitational tug on the quantum vacuum. It is like detecting the presence of an invisible planet by measuring the tiny wobble it induces in the orbit of a visible planet. You never see the invisible planet directly, but its influence is there, imprinted on the motion of things you can see. This is exactly how the top quark's existence was inferred, before it was directly discovered. Precision measurements of the W and Z bosons in the late 1980s and early 1990s showed tiny deviations from predictions that could only be explained if a very heavy quark existed. The mass of this undiscovered quark was predicted from the precision data to be roughly between 140 and 200 billion electron volts. When the top quark was finally produced directly at Fermilab in 1995, its measured mass was about 173 billion electron volts, right in the predicted range. Precision measurements had detected the top quark's fingerprint years before anyone actually saw it. The same approach was used to constrain the Higgs boson mass before its discovery. Precision measurements of the W boson, the Z boson, and the top quark, combined with the mathematical structure of the standard model, pointed to a Higgs boson mass in the range of roughly 115 to 150 billion electron volts. When the Higgs boson was found at 125 billion electron volts, it was once again right where precision measurements had indicated it should be. Now, the same strategy is being applied to search for whatever lies beyond the standard model. Physicists are measuring the properties of known particles. The W boson, the muon, the B mesons, the Higgs boson itself, with unprecedented accuracy. They are comparing these measurements to the standard model's predictions with excruciating care. And in several cases, the measurements are not quite matching the predictions. These discrepancies are small, they are subtle, they are at the edge of current experimental and theoretical precision. None of them, taken individually, is large enough to constitute a definitive discovery of new physics. But they are there. Multiple measurements, using different particles and different experimental techniques at different laboratories around the world, are finding tensions with standard model predictions. And the pattern of these tensions, the way they cluster and the direction they point, is making physicists take notice. Something may be hiding in the quantum vacuum. something that the standard model does not describe, something whose presence is being felt, faintly but persistently, in the most precise measurements humanity has ever made. The question is whether these small cracks in our most successful theory are genuine signals of a hidden layer beneath matter, or whether they will eventually be explained away by improved calculations and more data. That question is one of the central dramas of modern physics, and answering it requires looking very carefully at each of these anomalies, understanding what they mean, and honestly assessing what they tell us about the nature of reality. The Standard Model is often called the crown jewel of modern physics, and it has earned that title. But no matter how brilliant a theory is, nature always has the final word. And in recent years, nature has been whispering something that physicists cannot ignore. Not shouting, not screaming, whispering. Through small but persistent discrepancies between what the Standard Model predicts and what experiments actually measure. These whispers are coming from multiple directions, from different particles studied at different laboratories using entirely different techniques. And while no single whisper is loud enough to declare that the Standard Model is broken, the collective murmur is becoming harder and harder to dismiss. Let us examine these cracks one by one. Because understanding them, understanding exactly what has been measured and how it compares to what was expected, is essential for grasping why so many physicists believe that something is hiding beneath the Standard Model. And equally important, we need to be honest about what these measurements do and do not tell us. Because in physics, the line between a revolutionary discovery and a statistical mirage can be razor thin. Let us begin with one of the most dramatic and controversial results in recent particle physics: the mass of the W boson. The W boson is one of the two carrier particles of the weak nuclear force, discovered at CERN in 1983. It is heavy, roughly 80 times the mass of a proton, and it is unstable, decaying, almost instantly after being produced. The W boson is heavy, roughly 80 times the mass of a proton, and it is unstable, decaying almost instantly after being produced. But despite its brief existence, its properties can be measured with extraordinary precision because particle colliders produce millions of them. The Standard Model predicts the W boson's mass based on other measured quantities. Once you know the mass of the Z boson, the mass of the top quark, the mass of the Higgs boson, and the strength of the electromagnetic and weak forces, the Standard Model's mathematics locks in the W boson mass to a very specific value. There's almost no wiggle room. The predicted value is approximately 80,357 million electron volts, with an uncertainty of only about 6 million electron volts. That is a prediction accurate to roughly 1 part in 13,000. Making a measurement that precise is an extraordinary challenge, but that is exactly what several experimental collaborations have spent decades trying to do. For years, measurements from experiments at CERN's Large Electron Positron Collider, at Fermilab's Tevatron, and at the LHC itself had been broadly consistent with the Standard Model prediction. The measured values clustered around the predicted value with uncertainties that overlapped. Everything seemed to be in order. The Standard Model was holding. Then, in April of 2022, the CDF collaboration at Fermilab dropped a bombshell. The CDF detector had operated at the Tevatron Collider in Illinois until the machine was shut down in 2011. But the collaboration had spent the following decade painstakingly reanalyzing their data with improved techniques, better calibrations, and more sophisticated statistical methods. Their goal was to extract the most precise measurement of the W boson mass ever made from a hadron collider. And the result they published was stunning. The CDF measurement came in at approximately 80,433.5 million electron volts, with an uncertainty of only about 9.4 million electron volts. This was significantly higher than the standard model prediction, not slightly higher, not within the margin of error. The discrepancy between the CDF measurement and the standard model was about 7 standard deviations. In particle physics, a discrepancy of 5 standard deviations is considered the gold standard for claiming a discovery. 7 sigma is far beyond that threshold. If the CDF measurement was correct, it would be the clearest, most statistically significant evidence ever found that the standard model is incomplete. The physics world erupted. Hundreds of theoretical papers appeared within months, proposing explanations for the discrepancy. New particles, new forces, extended Higgs sectors with additional Higgs bosons, supersymmetric contributions, extra dimensions. The measurement, if correct, would require something beyond the standard model to explain it. Something that contributes to the W boson mass in a way the standard model does not account for. It was exactly the kind of crack in the perfect theory that physicists had been searching for. But there was a problem, and it was a serious one. Other experiments had also measured the W boson mass with high precision, and their results did not agree with CDF. The ATLAS experiment at CERN, using data from the LHC, published its own precision measurement of the W boson mass in March of 2024. The ATLAS result was approximately 80,366.5 million electron volts, with an uncertainty of about 15.9 million electron volts. This was in excellent agreement with the standard model prediction. It was also in significant tension with the CDF result. The two measurements, both claiming high precision, disagreed with each other by a substantial margin. Earlier, measurements from the LEP collider at CERN and from the D0 experiment at Fermilab, which operated alongside CDF at the Tevatron, were also broadly consistent with the standard model and inconsistent with the new CDF value. So the situation was not simply experiment versus theory. It was experiment versus experiment. Two groups of highly skilled physicists, both confident in their analysis, were getting different answers. This is an uncomfortable but not unprecedented situation in physics. Precision measurements are incredibly difficult. Measuring the W boson mass requires understanding your detector's response to exquisite accuracy. It requires knowing the energy scale of your detector to a fraction of a percent. It requires modeling the production of W bosons in proton collisions using theoretical calculations that themselves have uncertainties. Systematic errors, subtle biases in the measurement that are not captured by statistical uncertainties can creep in from dozens of sources. Identifying and eliminating these systematic errors is the central challenge of any precision measurement, and it is always possible that one experiment has underestimated its systematic uncertainties. As of now, the W boson mass discrepancy remains unresolved. The physics community has not reached a consensus on whether the CDF measurement or the ATLAS measurement is more reliable. Both collaborations stand behind their results. New measurements from the LHC, including from the CMS experiment and from LHCb, are expected in the coming years and should help clarify the situation. If future measurements confirm the CDF value, it will be revolutionary. If they confirm the Atlas value, the CDF result would likely be attributed to an unidentified systematic error. The answer matters enormously, but we do not have it yet. This uncertainty is frustrating, but it is also how science works. A single measurement, no matter how precise, is never enough. It must be confirmed independently. And when two precise measurements disagree, patience and additional data are required. The W boson mass puzzle is a work in progress, not a settled question. Now let us turn to another anomaly that has captivated the physics community for over 2 decades. The anomalous magnetic moment of the muon. The muon is a particle closely related to the electron. It has the same electric charge, the same spin, and interacts through the same forces. But it is about 207 times heavier. This extra mass makes the muon particularly sensitive to the influence of heavy unknown particles lurking in the quantum vacuum, which is why measuring its properties with extreme precision is such a powerful way to search for new physics. Like the electron, the muon behaves as a tiny magnet due to its electric charge and spin. The strength of this internal magnet is described by a quantity called the magnetic moment. Basic quantum mechanics predicts a specific value for the muon's magnetic moment, but this prediction is only approximate. When you account for the muon's interactions with the quantum field surrounding it, with the virtual particles constantly popping in and out of existence in the vacuum, the magnetic moment changes by a small amount. This correction is called the anomalous magnetic moment, and it is usually written as the quantity G-2 divided by 2, often abbreviated simply as G-2. The standard model predicts G-2 with extraordinary precision. The calculation includes contributions from electromagnetism, from the weak force, and from the strong force. The electromagnetic contributions are the most straightforward and have been calculated to incredible accuracy, with terms computed through 5 loops of virtual particle exchanges. The weak force contributions are smaller but well understood. The strong force contributions are the most troublesome, and we will return to them shortly. The first modern precision measurement of the muon's anomalous magnetic moment was performed at Brookhaven National Laboratory on Long Island, New York. The experiment used a large superconducting magnetic ring, roughly 15 meters in diameter, to store muons traveling at relativistic speeds. By measuring how quickly the muon's spin direction rotated relative to its direction of motion as it circled the ring, experimenters could extract G-2 with remarkable precision. The Brookhaven experiment published its final result in 2006, and it showed a discrepancy with the standard model prediction of about 3.7 standard deviations. Intriguing, suggestive, but not definitive. 3.7 sigma could be a real signal of new physics, or it could be a statistical fluctuation that would disappear with more data. To settle the question, the entire magnetic storage ring, a 50-ton superconducting magnet, was transported from Long Island to Fermilab in Illinois in 2013. This was an extraordinary logistical feat. The ring was too fragile to be taken apart and reassembled, so it had to be moved in one piece. It traveled by barge down the East Coast, through the Gulf of Mexico, up the Mississippi River, and then by truck along highways in the middle of the night, escorted by police. The journey covered over 3,200 miles and took over a month. At Fermilab, a new collaboration called the muon G-2 experiment rebuilt the infrastructure around the ring and began taking fresh data in 2018 with a far more intense muon beam than was available at Brookhaven. Their results have been published in stages. The first result, announced in April of 2021, confirmed the Brookhaven measurement with improved precision. Subsequent results published in 2023 further tightened the measurement. When the Fermilab collaboration announced its first result in 2021, the combined experimental value from Brookhaven and Fermilab showed a discrepancy with the traditional standard model prediction of about 4.2 standard deviations, close to the 5 sigma discovery threshold, suggestive but not quite definitive, and subsequent Fermilab results, including the collaboration's final measurement published in June of 2025 with a precision of 127 parts per billion, confirmed the experimental value and pushed it even further from the traditional theoretical prediction. That should have been the moment the standard model cracked, but the situation turned out to be far more nuanced than that, because the standard model prediction itself became a subject of intense debate. The problem lies with the strong force contributions to G-2. When the muon interacts with the quantum vacuum, some of the intermediate virtual processes involve quarks and gluons, which interact through the strong nuclear force. The strong force, described by a theory called quantum chromodynamics, is notoriously difficult to calculate at low energies because the force becomes so powerful that the usual approximation techniques used in particle physics break down completely. You cannot simply compute a series of increasingly small corrections as you can with electromagnetism. The mathematics becomes intractable. There are 2 main approaches to handling these strong force contributions. The first approach uses experimental data. Specifically, it uses measurements of how electrons and positrons annihilate into hadrons, which are particles made of quarks at various energies. These measurements can be mathematically related to the strong force contribution to the muon's magnetic moment through a technique called a dispersion relation. This data-driven approach has been the standard method for decades and produces a prediction that disagrees with the Fermilab measurement at the 5 sigma level. The second approach uses lattice quantum chromodynamics. This is a computational technique where the equations of the strong force are solved numerically on a discrete grid of space-time points using powerful supercomputers. You essentially simulate the behavior of quarks and gluons from first principles without relying on any experimental input. Lattice calculations have improved dramatically in recent years as computing power has increased and algorithmic techniques have been refined. And here is the complication. Recent lattice calculations, performed by several independent groups around the world, produce a standard model prediction for G-2 that is closer to the experimental measurement than the data-driven prediction. If the lattice calculations are correct, the discrepancy between theory and experiment shrinks substantially, perhaps even to the point where there is no significant anomaly at all. So the central question becomes not just whether the experiment is right, but which theoretical calculation is right. The data-driven approach and the lattice approach should, in principle, give the same answer, since they are both trying to calculate the same physical quantity. The fact that they currently disagree suggests that either one or both of them has an unidentified systematic error, or that there is something subtle about the strong force at low energies that is not being correctly captured by one of the methods. In 2025, both sides of this story reached a climax. In May, the Theory Initiative published an updated prediction that incorporated recent lattice calculations alongside the traditional data-driven approach. The new theoretical value shifted significantly closer to the experimental measurement. Then, in June, the Fermilab collaboration published its final result, the most precise measurement of the muon's magnetic moment ever made. The experimental number held firm, but with the theory now moving toward it, the gap between prediction and measurement has narrowed dramatically. What once looked like a 5 sigma crack in the standard model now appears severely undermined, though not yet definitively resolved. The data-driven and lattice approaches still disagree with each other at the level of about 3 standard deviations, and until that internal theoretical tension is understood, the door to new physics from muon G-2 cannot be fully closed, but it is no longer wide open. Let us now examine a third area where intriguing hints have emerged: the decays of B mesons. B mesons are particles that contain a bottom quark, also called a beauty quark, paired with a lighter quark. They are produced in enormous quantities at the LHC, and their decays provide a rich testing ground for the standard model. The LHCb experiment at CERN is specifically designed to study the properties and decays of B mesons and other particles containing heavy quarks. Its detector is optimized for identifying the tracks and decay products of these particles with extraordinary precision. One of the fundamental predictions of the standard model is a property called lepton universality. This states that the 3 charged leptons, the electron, the muon, and the tau, are identical in every respect except for their masses. The weak force treats them all the same. This means that in certain B meson decays, after you account for the mass differences between the leptons, the probability of the decay producing a muon pair should be the same as the probability of it producing an electron pair. This ratio should be exactly 1. Starting around 2014, the LHCb experiment began reporting measurements of these ratios that appeared to deviate from 1. The ratio called R sub k, which compares certain B meson decays involving muon pairs to those involving electron pairs, consistently came in slightly below 1. The ratio R sub k star, a related measurement involving a different decay channel, showed a similar pattern. Each individual measurement deviated from the standard model prediction by roughly 2 to 3 standard deviations. Not enough to claim a discovery from any single result, but the pattern was striking. Multiple related measurements, all pointing in the same direction, all suggesting that the weak force might not treat electrons and muons identically after all. This generated enormous theoretical excitement. If lepton universality was truly violated, it would be unambiguous evidence for new physics. The standard model does not contain any mechanism that could cause such a violation at measurable levels. Theorists proposed new heavy particles called leptoquarks that couple differently to different lepton generations. They proposed new Z-prime bosons, heavier cousins of the Z boson with flavor-dependent interactions. Hundreds of papers explored the theoretical implications. But then came a crucial update. In December of 2022, LHCb published a revised measurement of R sub k and R sub k star using their full dataset and significantly improved analysis techniques. The new results were consistent with consistent with the standard model. The earlier anomaly, which had persisted for nearly a decade and generated hundreds of theoretical papers, appeared to have been largely a product of systematic effects in the earlier analyses that had not been fully accounted for. This was a sobering lesson for the entire field. It demonstrated how carefully results at the 2 to 3 sigma level must be interpreted. At that level of statistical significance, random fluctuations and subtle systematic effects can masquerade as signals of new physics. The history of particle physics contains numerous examples of anomalies at 2 to 3 sigma that initially seemed compelling but eventually disappeared with more data or improved analysis. The pentaquark claims of the early 2000s. Various reported violations of Lorentz invariance, anomalies in top quark, production asymmetries, all were initially exciting and all eventually faded away. However, and this is important, the story of B meson anomalies is not entirely over. While the R sub k and R sub k star ratios have moved closer to standard model predictions, other measurements in B meson physics continue to show tensions. Angular distributions in certain B meson decays, described by a set of observables that physicists label with names like P5', still deviate from standard model predictions at levels that are difficult to explain as pure statistical noise. Certain branching ratios, which measure the probability that a B meson decays through a specific channel, also show persistent tensions with calculations. These remaining tensions are at the level of 2 to 4 standard deviations individually. None is conclusive on its own, but the pattern persists across multiple decay channels and multiple observables, and the direction of the deviations is broadly consistent with what certain new physics models would predict. Global analyses that combine all available B meson data still show a moderate preference for new physics contributions over the pure standard model, typically at the 3 to 4 sigma level when all data are combined. The situation is thus nuanced. The most celebrated B meson anomaly, the violation of lepton universality in R sub k, has largely evaporated, but a broader pattern of tensions in B meson decays remains. Whether this broader pattern represents a genuine signal of new physics or a combination of statistical fluctuations and theoretical uncertainties in the standard model predictions remains an open question. More data from the ongoing LHC run and improved theoretical calculations will be needed to resolve it. Beyond these specific anomalies, there are fundamental phenomena that the standard model simply cannot explain at all. These are not subtle discrepancies requiring precision measurements to detect. They are glaring holes in our understanding that are visible to anyone who looks. Dark matter is perhaps the most dramatic example. The evidence for dark matter comes from multiple independent astronomical and cosmological observations. Galaxies rotate in ways that can only be explained if they contain far more mass than the visible stars and gas account for. Galaxy clusters are held together by gravitational forces, far stronger than what their visible matter could produce. The cosmic microwave background, the faint afterglow of the Big Bang, contains patterns that can only be explained if the early universe contained a significant amount of non-luminous, non-baryonic matter. Gravitational lensing, the bending of light from distant galaxies by intervening mass, reveals mass distributions that do not correspond to any visible matter. All of this evidence points to the same conclusion. About 27% of the total energy content of the universe consists of matter that does not interact through electromagnetism. It does not emit light. It does not absorb light. It does not reflect light. It interacts gravitationally, and possibly through the weak nuclear force, but it is completely invisible to every telescope and detector that relies on electromagnetic radiation. And none of the 17 particles in the Standard Model can account for it. Whatever dark matter is, it is made of something the Standard Model does not describe. The matter-antimatter asymmetry is another profound puzzle. The laws of physics, as described by the Standard Model, are very nearly symmetric between matter and antimatter. For every process that creates matter, there is a corresponding process that creates antimatter at almost exactly the same rate. The Big Bang should therefore have produced equal amounts of matter and antimatter, and when matter and antimatter meet, they annihilate completely, converting their combined mass into pure energy. If equal amounts had been produced and then annihilated, the universe would contain nothing but radiation. No atoms, no stars, no planets, no people. Yet here we are. The universe is overwhelmingly made of matter. Antimatter is extraordinarily rare. Something in the first moments after the Big Bang must have favoured matter over antimatter by a tiny but crucial amount. The Standard Model does contain a mechanism for this asymmetry called CP violation, which refers to a subtle difference in how certain processes behave when you swap particles with antiparticles and mirror reflect them in space. CP violation has been measured experimentally and is real, but the amount of CP violation in the Standard Model is far too small to explain the observed matter-antimatter imbalance. The Standard Model falls short by many orders of magnitude. Something else, some additional source of CP violation beyond the Standard Model, must be responsible. Then there are neutrino masses. The original Standard Model assumed neutrinos were massless. This was consistent with all experimental data available at the time. But starting in the late 1990s, experiments in Japan, Canada, and elsewhere demonstrated conclusively that neutrinos oscillate. They transform from one type to another as they travel through space. An electron neutrino produced in the Sun can arrive at Earth as a muon neutrino or a tau neutrino. This oscillation is only possible if neutrinos have mass. The discovery was recognized with the Nobel Prize in Physics in 2015, awarded to Takaaki Kajita and Arthur MacDonald. Neutrino masses can be accommodated in the Standard Model by adding new terms to the equations. But the masses themselves are mysterious. They are incredibly tiny, less than 1/1,000,000th the mass of an electron. Why are they so small compared to the masses of all other known particles? The Standard Model offers no explanation, and the mechanism by which neutrinos acquire mass might be fundamentally different from the Higgs mechanisms that gives mass to other particles. Some models propose that neutrinos are their own antiparticles, a property called Majorana mass, which would make them unique among all known fundamental particles. Experiments are currently searching for evidence of this possibility through a rare process called neutrinoless double beta decay. If observed, it would be a clear sign of physics beyond the Standard Model. And finally, there is gravity. The Standard Model describes 3 of the 4 known forces beautifully, but gravity, the force that governs the motion of planets, the collapse of stars, the expansion of the universe, the very structure of space-time itself, is entirely absent. Einstein's general theory of relativity describes gravity as the curvature of space-time caused by mass and energy. It is a classical theory, not a quantum theory. When physicists try to apply quantum mechanical methods to gravity using the same techniques that work brilliantly for the other three forces. The mathematics produces infinities that cannot be removed. The theory breaks down. Gravity and quantum mechanics, the two pillars of modern physics, are fundamentally incompatible in their current formulations. A quantum theory of gravity, one that unifies general relativity with quantum mechanics, remains one of the greatest unsolved problems in all of science. So here is the picture that emerges when you step back and look at everything together. The Standard Model is spectacularly successful within its domain. Every particle it predicts has been found. Its calculations agree with experiment to breathtaking precision. It is the most thoroughly tested and precisely confirmed theory in the history of science. But it is also clearly, undeniably incomplete. It cannot explain dark matter, which makes up more than 5 times as much of the universe as ordinary matter. It cannot explain the matter-antimatter asymmetry that is responsible for the existence of everything we see. It cannot explain why neutrinos have mass or why those masses are so absurdly small. It has nothing to say about gravity, and precision measurements are revealing small but persistent cracks, discrepancies between prediction and observation that might be the first fingerprints of whatever lies beyond. These cracks do not yet constitute a confirmed discovery. The W boson mass discrepancy is confused by contradictory experimental results. The muon G-2 anomaly depends on which theoretical calculation you trust. The B meson anomalies have partially receded, though broader tensions remain. None of this is the clean, unambiguous signal that physicists dream of. But the pattern is suggestive. Multiple independent measurements, probing different particles through different forces, using different experimental techniques, are finding tensions with the Standard Model. Some of these tensions might be statistical fluctuations that will vanish with more data. Some might be caused by unidentified, systematic errors in the experiments or uncertainties in the theoretical calculations. But it is becoming increasingly difficult to explain all of them away simultaneously. The probability that every single one of these tensions is a meaningless coincidence becomes smaller and smaller as more of them accumulate. Something appears to be there, just beneath the surface, just beyond the reach of current experiments. A hidden structure that is gently tugging on the properties of known particles, leaving faint but detectable traces in the most precise measurements ever made. The Standard Model describes the world we can see with extraordinary accuracy, but it appears to be sitting on top of something deeper. Something it does not describe. Something that, once revealed, might transform our understanding of matter and forces and fields as profoundly as the discovery of quarks transformed our understanding of the atomic nucleus. The question is what that something is. And answering that question is the great quest of 21st century physics. So, what could be down there? What lies beneath the Standard Model? What hidden structure could be responsible for the anomalies, the unexplained masses, the dark matter, the missing antimatter? These are not idle questions. They are among the most important questions in all of science. And physicists have been thinking about them for decades, long before the current generation of anomalies appeared. Because the Standard Model, even at the height of its success, has features that look like clues, properties that seem to be pointing at something deeper, patterns that beg for explanation. Consider the particles themselves. The Standard Model contains 6 quarks and 6 leptons, arranged in 3 generations. The first generation, the up quark, the down quark, the electron, and the electron neutrino, makes up all ordinary matter. Every atom in your body, every star in the sky, every planet and moon and asteroid is built from first-generation particles. The second and third generations are heavier copies of the first. The charm quark is like a heavier up quark. The strange quark is like a heavier down quark. The muon is like a heavier electron, and so on. These heavier particles are unstable. They decay rapidly into first-generation particles. They appear only in high-energy collisions or in certain rare decays. They play almost no role in the everyday world. So why do they exist? Why are there 3 generations instead of 1? Why not 2? Why not 4? The Standard Model offers no answer. It simply accepts the existence of 3 generations as a fact to be plugged in, not explained. The theory describes how these particles behave with extraordinary precision, but it does not explain why nature chose this particular set of building blocks. This is like having a recipe that tells you exactly how to bake a cake, but offers no explanation for why you are using flour, sugar, and eggs rather than some entirely different set of ingredients. The recipe works perfectly, but you sense that there must be a reason behind it. A deeper logic that the recipe itself does not capture. Then there is the mystery of the masses. The 17 particles in the Standard Model have wildly different masses, and no one knows why. The top quark is roughly 340,000 times heavier than the electron. The tau neutrino, the heaviest neutrino, has a mass less than 1/1,000,000th that of the electron. The range of masses spans at least 12 orders of magnitude, from the almost massless neutrinos to the enormously heavy top quark. The Higgs mechanism explains how particles acquire mass. It tells you that mass comes from interaction with the Higgs field, but it does not tell you why different particles interact with the Higgs field at such dramatically different strengths. The strengths of these interactions are among the free parameters of the Standard Model, numbers that must be measured experimentally because the theory cannot predict them. The Standard Model contains roughly 25 of these free parameters. The masses of the quarks and leptons, the strengths of the 3 forces, the parameters describing how quarks mix with each other and how neutrinos mix with each other, the mass of the Higgs boson, the vacuum energy density. These are all numbers that the Standard Model needs in order to make predictions but cannot calculate from first principles. They are inputs, not outputs, and many physicists find 25 unexplained inputs deeply unsatisfying. A truly fundamental theory, they argue, should predict these numbers, or at least reduce them to a smaller set of more basic quantities. Having so many free parameters is a strong hint that the Standard Model is not the final story. It is an effective description of something deeper, like Newtonian gravity, which works beautifully for everyday purposes, but is actually an approximation to the curved space-time of general relativity. The Standard Model may work beautifully within its domain, while missing the deeper truth that determines those 25 numbers. Perhaps the most tantalizing hint of deeper structure comes from the forces themselves. The 3 forces in the Standard Model, electromagnetism, the weak nuclear force, and the strong nuclear force, each have different strengths at the energies we can access in laboratories. The strong force is the strongest, roughly 100 times more powerful than electromagnetism at nuclear distances. Electromagnetism is stronger than the weak force at low energies, because the W and Z bosons that carry the weak force are so heavy that they suppress its range and effective strength. But the strengths of these forces are not fixed. They change with energy. This is one of the most remarkable predictions of quantum field theory, and it has been confirmed experimentally. As you probe matter at higher and higher energies, corresponding to shorter and shorter distances, the effective strength of the strong force decreases, while the effective strength of electromagnetism increases slightly. The weak force also changes, and when you extrapolate these running couplings to extremely high energies, something extraordinary happens. The three forces converge. Their strengths approach each other. In the Standard Model alone, the three forces come close to meeting at a single point but do not quite converge. They miss each other slightly, arriving at nearly but not exactly the same strength at an energy scale of roughly 10 to the power of 15 billion electron volts. This near convergence could be a coincidence. Three lines drawn on a graph might happen to nearly intersect without any deeper significance. But physicists have long suspected it is more than coincidence. It looks like a clue. It looks like the three forces are trying to tell us that at some very high energy scale, far beyond what any current experiment can reach, they merge into a single unified force, described by a single mathematical symmetry. This idea is called grand unification, and the theoretical frameworks that describe it are called grand unified theories. In a grand unified theory, the three separate forces of the Standard Model are different low-energy manifestations of one underlying force, just as electricity and magnetism, which appear to be separate phenomena in everyday life, were revealed by James Clerk Maxwell in the 1860s to be two aspects of one unified electromagnetic force. Grand unification would represent a similar leap, but far more dramatic. Not two forces merging into one, but three. Grand unified theories also predict that quarks and leptons, which appear so different at everyday energies, are actually different aspects of the same underlying objects. At very high energies, above the unification scale, a quark could transform into a lepton and vice versa. The boundary between the particles that feel the strong force and those that do not would dissolve. Everything would be unified into a single family of particles interacting through a single force. This has a dramatic consequence. If quarks can transform into leptons, then protons are not truly stable. A proton contains quarks. If one of those quarks can turn into a lepton through a process mediated by the unified force, the proton would decay. It would disintegrate, its quarks rearranging and transforming until the proton is gone, replaced by lighter particles. The predicted lifetime of the proton in most grand unified theories is staggeringly long, somewhere between 10 to the power of 34 and 10 to the power of 36 years. The universe is only about 10 to the power of 10 years old. So the probability of any individual proton decaying in any reasonable observation period is vanishingly small. But you can compensate for this tiny probability with enormous numbers. The Super Kamiokande detector in Japan watches a tank containing 50,000 tons of ultra-pure water. Each water molecule contains 10 protons. The total number of protons being monitored is roughly 7.5 times 10 to the power of 33. By watching this, many protons simultaneously for years, you have a reasonable chance of catching one in the act of decaying. So far, after more than 2 decades of observation, no proton decay has been detected. This null result sets a lower limit on the proton lifetime of about 10 to the power of 34 years for the most commonly predicted decay mode. This rules out some of the simpler grand unified theories. but many more sophisticated versions remain viable with predicted lifetimes just beyond the current experimental reach. The next generation of experiments, including the Deep Underground Neutrino experiment in the United States and the Hyper Kamiokande detector in Japan, will push the sensitivity further, watching even more protons for longer periods with better detection capabilities. If proton decay is observed, it would be one of the most profound discoveries in the history of physics. It would confirm that the forces are unified, that quarks and leptons are related, that the standard model is part of a grander structure. If proton decay continues to elude detection, it would constrain grand unified theories further, but would not eliminate them entirely, since many models predict lifetimes that are simply too long for current or near-future experiments to probe. There is a way to make grand unification work more naturally, and it involves one of the most discussed extensions of the standard model: supersymmetry. Supersymmetry proposes a deep mathematical symmetry between the two fundamental categories of particles: fermions, which have half-integer spin and include quarks and leptons, and bosons, which have integer spin and include the force carriers and the Higgs boson. In a supersymmetric theory, every known particle has a partner of the opposite type. Every fermion has a boson partner and every boson has a fermion partner. The electron would have a boson partner called the selectron. The muon would have the smuon. Each quark would have a squark. The photon would have a fermion partner called the photino. The gluon would have the gluino. The Higgs boson would have the Higgsino. For every particle we know, there would be a shadow particle we have not yet seen. If supersymmetry were exact, these partner particles would have exactly the same mass as their standard model counterparts. But we have not observed any of them, which means if supersymmetry exists in nature, it must be a broken symmetry. The partner particles must be heavier, pushed to higher masses by whatever mechanism breaks the symmetry. The question of how much heavier determines whether current or future experiments can find them. Supersymmetry is attractive for several compelling reasons. First, it makes grand unification work. When you add the supersymmetric partner particles to the calculation of how the force strengths change with energy, the three forces converge much more precisely at a single point. The near miss in the standard model becomes an almost exact meeting. This is not a guarantee that supersymmetry is correct, but it is a striking piece of circumstantial evidence. Second, supersymmetry addresses the hierarchy problem. The Higgs boson has a measured mass of about 125 billion electron volts, but in the standard model, quantum corrections from virtual particles should drive the Higgs mass up to enormously higher values, close to the Planck scale where gravity becomes important, roughly 10 to the power of 19 billion electron volts. Keeping the Higgs mass at its observed value requires an extraordinarily precise cancellation between different quantum corrections, a fine-tuning of roughly 1 part in 10 to the power of 30. This level of fine-tuning seems unnatural. Supersymmetry provides a natural mechanism for this cancellation. The quantum corrections from standard model particles are automatically cancelled by the corrections from their supersymmetric partners. The cancellation is built into the mathematical structure of the theory, no fine-tuning required. Third, supersymmetry provides a natural candidate for dark matter. In many supersymmetric models, a symmetry called R parity ensures that the lightest supersymmetric particle is stable. It cannot decay into anything lighter because there is nothing lighter with the right quantum numbers. This particle would be electrically neutral, would interact only weakly with ordinary matter, and would have been produced in the early universe in quantities consistent with the observed dark matter abundance. It would be invisible to telescopes, detectable only through its gravitational effects. This matches the observed properties of dark matter remarkably well. The Large Hadron Collider has searched extensively for supersymmetric particles. Both ATLAS and CMS have conducted hundreds of separate analyses, looking for the distinctive signatures that supersymmetric particles would produce when created in proton collisions. These signatures include events with large amounts of missing energy, where the invisible supersymmetric particles carry energy out of the detector without leaving a trace. They include events with unusual combinations of jets and leptons that would be produced when heavy supersymmetric particles decay through cascades of lighter particles. Every possible signature has been searched for, and so far, nothing has been found. This absence of evidence has pushed the minimum possible masses for supersymmetric particles steadily upward. Gluinos, if they exist, must be heavier than roughly 2.3 trillion electron volts. Quarks must be heavier than roughly 1.8 trillion electron volts. The constraints on other supersymmetric particles vary, but are generally in the range of several hundred billion to over a trillion electron volts. These limits are significantly higher than what many theorists had originally expected. In the 1990s, when supersymmetry was at the peak of its theoretical popularity, many physicists expected that supersymmetric particles would be found almost immediately once the LHC turned on. The fact that they have not been found has led to serious soul-searching within the theoretical physics community. Some physicists have concluded that supersymmetry is simply not realized in nature, and that alternative explanations for the hierarchy problem, dark matter, and force unification must be sought. Others maintain that supersymmetric particles exist, but are simply heavier than the LHC can produce, and that a more powerful collider would find them. The debate is ongoing and sometimes heated. There are other ideas for what might lie beneath the standard model. Some theorists propose that the Higgs boson is not a fundamental particle at all. Instead of being an elementary ripple in a fundamental Higgs field, it might be a composite object, made of a more fundamental constituents bound together by a new, undiscovered force. This idea is analogous to how pions, which were once thought to be fundamental, turned out to be composites made of quarks. If the Higgs boson is composite, there would be an entire new layer of structure beneath it. New fundamental particles, a new binding force, a whole new sector of physics waiting to be uncovered. The LHC is searching for signs of Higgs compositeness by measuring the Higgs boson's interactions with extreme precision. Any deviation from the standard model prediction for these interactions could indicate that the Higgs is not elementary. Extra dimensions represent another possibility. Our everyday experience involves 3 dimensions of space and 1 of time. But several theoretical frameworks, including string theory, propose that additional spatial dimensions exist that we cannot directly perceive. These extra dimensions might be curled up at incredibly small scales, far too tiny for any experiment to resolve. Or they might be large but inaccessible to ordinary matter, with our entire observable universe confined to a 3-dimensional membrane, called a brane, floating in a higher dimensional space. If extra dimensions exist, they could explain several puzzles. They could explain why gravity is so much weaker than the other forces. Gravity might be just as strong as the others, but its strength gets diluted because it alone can spread into the extra dimensions. The LHC has searched for evidence of extra dimensions through various signatures, including the production of microscopic black holes and the observation of particles disappearing into extra dimensions. So far, no evidence has been found, but the searches continue with each new dataset. While the search for new particles continues, CERN is also directly hunting for dark matter. If dark matter particles interact with ordinary matter through any force besides gravity, even extremely weakly, they could potentially be produced in LHC collisions. The experimental signature would be distinctive. A collision would produce visible particles that are detected normally, but the total energy and momentum of those visible particles would not balance. Some energy and momentum would be missing, carried away by invisible dark matter particles that passed through the detector without interacting. Both ATLAS and CMS search for this missing energy signature in every dataset they collect. So far, no significant excess of missing energy events beyond standard model predictions has been observed. This places constraints on dark matter candidates, ruling out certain mass ranges and interaction strengths. But it does not rule out dark matter production at the LHC entirely. Dark matter might simply be heavier than the LHC can produce, or it might interact so weakly that the production rate is below the current sensitivity. The immediate future of this search lies with the high luminosity Large Hadron Collider. This major upgrade, currently under construction at CERN and expected to begin operation around mid-2030, will increase the collision rate by a factor of 5 to 7 beyond the original LHC design. Over its projected lifetime, the high luminosity LHC will accumulate roughly 10 times more data than the LHC has collected in its entire operating history to date. This enormous increase in data will push precision measurements to new levels. Properties of the Higgs boson that are currently measured with uncertainties of 10 or 20% will be nailed down to a few percent or better. Rare decay modes that have never been observed will become accessible, and the sensitivity to new particles, whether supersymmetric partners, dark matter candidates, or something entirely unexpected, will extend to higher masses and weaker interaction, strengths than ever before. One of the most important measurements the high luminosity LHC will pursue is the Higgs boson self-coupling. This quantity describes how strongly the Higgs boson interacts with itself, and it is directly related to the shape of the Higgs field's potential energy function. The shape of this potential determines the stability of the vacuum itself. Whether the current state of the universe is truly stable or merely metastable, meaning it could, in principle, tunnel to a lower energy state with catastrophic consequences, depends on the precise value of the Higgs self-coupling. The standard model predicts a specific value. Measuring it and finding a deviation would be strong evidence for new physics influencing the Higgs sector. Beyond the high luminosity LHC, physicists are planning even more ambitious machines. The most advanced proposal at CERN is the Future Circular Collider. This would be a new tunnel roughly 91 kilometers in circumference, more than 3 times the size of the current LHC tunnel. In its first phase, planned for the 2040s, it would collide electrons and positrons at energies precisely tuned to produce enormous numbers of Higgs bosons, Z bosons, and W bosons. This would allow measurements of their properties with a precision roughly 10 times better than the high luminosity LHC can achieve. In a later phase, the same tunnel would house a proton-proton collider, reaching energies of approximately 100 trillion electron volts, roughly 7 times higher than the LHC. This would dramatically extend the direct search for new particles, probing energy scales that are completely inaccessible today. China has proposed a similar machine called the Circular Electron-Positron Collider, which could begin operation in the mid-20s. Japan has proposed the International Linear Collider, a straight-line accelerator using a different approach to achieve exquisite precision in electron-positron collisions. Each of these proposals has different strengths and different timelines, but they all share the same fundamental goal: to probe the structure of matter at deeper levels than any experiment has reached before. And this brings us to the deepest question of all, the question that has driven physics forward through every revolution, every paradigm shift, every moment when we thought we had reached the bottom only to discover another layer beneath. Is this truly the end? Are the quantum fields of the Standard Model genuinely fundamental? Or are they themselves manifestations of something even more basic? Something we have not yet imagined? Every time in the history of physics that we believed we had found the fundamental constituents of matter, we were wrong. Atoms were supposed to be uncuttable. They were not. Protons and neutrons were supposed to be elementary. They were not. At each level, what appeared to be the bottom turned out to be a surface with richer and stranger structure hiding underneath. Is there any reason to believe that quarks and electrons and the Higgs boson are truly where the story ends? We do not know. No experiment has found any evidence that quarks or electrons have internal structure down to the smallest distances currently accessible, roughly 1,000th the diameter of a proton. But the absence of evidence at the scales we can probe does not mean there is no structure at smaller scales. It just means we have not looked deeply enough yet. String theory proposes that all particles are different vibration modes of one-dimensional strings at a scale of roughly 10 to the power of negative 35 meters. Probing that scale directly would require energies vastly beyond anything achievable with foreseeable technology. But indirect evidence, through precision measurements, through the discovery of patterns that only make sense if string theory or some similar framework is correct, might be within reach. What we can say with confidence is this: the Standard Model is not the final theory. It works brilliantly within its domain. The gaps we explored earlier, the dark matter that holds galaxies together, the missing antimatter, the unexplained neutrino masses, the absence of gravity from the quantum picture, all remain wide open. And it contains roughly 25 unexplained parameters that cry out for a deeper explanation. These are not minor imperfections. They are fundamental features of an incomplete theory. The pattern of evidence, the cracks in precision measurements, the unexplained phenomena, the mathematical hints from force unification, all of it points in the same direction. The Standard Model is an effective theory, an extraordinarily successful approximation to a deeper reality. Like Newtonian mechanics before it, the Standard Model captures the behavior of nature within a certain regime with breathtaking accuracy. But it is not the whole story. There is more beneath. Matter is layered. We have known this for over a century. Molecules are made of atoms. Atoms are made of electrons and nuclei. Nuclei are made of protons and neutrons. Protons and neutrons are made of quarks. And all of these particles are ripples in quantum fields that fill all of space. Each layer was hidden until we developed the tools to see it. Each layer was stranger and more beautiful than the one above. And the evidence strongly suggests that at least one more layer remains hidden, waiting in the quantum vacuum, leaving its fingerprints on precision measurements, manifesting as dark matter that holds galaxies together, whispering through anomalies that do not quite fit the standard model. The experiments at CERN and at laboratories around the world are humanity's attempt to peel back this next layer. Every collision at the LHC is a question posed to nature. Every measurement is a test of our deepest understanding. And somewhere in the data, somewhere among the billions of collisions recorded every day, the patterns of decay, the precise masses and interaction strengths and quantum numbers, the answer is hiding. It may take years to find. It may take decades. It may require machines far more powerful than anything that exists today. But the direction is clear. We are going deeper. We have always gone deeper. And we will continue going deeper because that is what humans do. We look at the world around us and we ask what it is made of. And then we build the tools to find out. Every great discovery in physics has followed this pattern. We build better instruments. We measure more carefully. We look more closely. And we find something we did not expect. The electron was unexpected. The nucleus was unexpected. Quarks were unexpected. The Higgs boson, though predicted, confirmed a mechanism so profound that its implications are still being explored. The next surprise is out there. It might be supersymmetric particles, or extra dimensions, or composite Higgs constituents, or something so strange that nobody has thought of it yet. History suggests that the actual answer will be the last of these. The universe has consistently been stranger than even our most creative theorists imagined. So the next time you pick up a glass of water, or touch a table, or simply look at your own hand, remember what lies beneath. Beneath the surface you feel, there are molecules. Beneath the molecules, atoms. Beneath the atoms, electrons and nuclei. Beneath the nuclei, quarks and gluons. Beneath the quarks and gluons, quantum fields stretching across all of space, vibrating, interacting, giving rise to everything you see and touch and are. And beneath those fields, there appears to be something else, something we have not yet fully grasped. A hidden layer of reality that manifests as dark matter, as unexplained masses, as tiny anomalies in the most precise measurements ever performed. A deeper architecture that shapes the universe from the inside. You are made of this. Whatever is down there at the deepest level of reality, you are built from it. The quarks in your atoms are held together by the strong force. The electrons in your atoms interact through the electromagnetic force. The nuclear reactions that power the sun and warm your planet operate through the weak force and the strong force together. The Higgs field is giving mass to every particle in your body right now, at this very moment, as you listen to these words. And if there are additional fields, additional forces, additional particles that we have not yet discovered, they are also there, inside you, influencing the matter you are made of in ways too subtle for our current instruments to detect, but real nonetheless. The universe is built on hidden structure. Every layer we have peeled back has revealed something deeper, something more fundamental, something more astonishing than what came before. And the search for the next layer is underway. The collisions continue, the data accumulate, the calculations grow more precise, And somewhere in that vast ocean of information, the next revolution in our understanding of matter is waiting to be found. We are made of atoms that are made of quarks that are ripples in fields that fill all of space. And those fields appear to be sitting on top of something we have not yet seen. The hidden layer beneath matter. It is there. We can feel its influence. And we are closing in. Thank you for joining me on this journey into the heart of matter. If you found this exploration valuable, a like or subscribe would mean a lot. It helps me keep making these deep explorations of the universe and our place in it. And remember, the next time you look at anything at all, you are looking at quantum fields, fields that fill all of space, fields that may be hiding something extraordinary just beneath their surface, something that the most powerful scientific instruments ever built are working right now to reveal. Good night. And may you never look at matter the same way again